Now that we've talked a bit about configuring the common fork join pool conceptually, and I talked about the pros and cons of different approaches, let's demonstrate how to actually configure it in practice. And this particular example is here in my EX20 folder, and it basically shows the performance impact. It quantifies the performance impact of configuring the common fork join pool size either adaptively or non-adaptively. So as I mentioned before, you can control the common fork join pool size programmatically. You can do it a couple different ways. We're primarily going to focus here on applying the ManagedBlocker interface, which allows the common fork join pool to adaptively and dynamically add new worker threads as other threads block. So it'll keep growing. And the particular example we'll look at, we'll actually walk through the code in a bit of detail, but it's called test download behavior. And it's going to pass in a function that will be parameterized in a very cool way using Java functional behavioral parameterization, and allows us to be able to download and store images from remote websites using different strategies. So this is basically the good old strategy pattern from the Gang of Four book. And as you'll see here, as when I walk through the code in a second, you'll see that there's a couple of different techniques. You'll see that we use something called the default download behavior, which doesn't do any adaptive use of adding more threads to the thread pool. And so it'll download and store some number of images using 12 threads in the pool, because that's what the default was. This was running on an older MacBook than the one I have now, which only had 6 cores, now I have 8 cores. So you'll see the little different behavior when we run this in a minute. And then we're going to test a couple of other examples that download and store these images. And there's basically this adaptive behavior that grows the number of threads in the pool. And as is often the case, the adaptive stuff will perform better. And the reason it performs better is it's able to do more things in parallel, because it's not limited to the number of threads that are the default number. It grows them, and therefore you can get more work done because there's more computation that can be taking place. And you can take a look at this code, which we will walk through here right now. So here's the code we're talking about. This is in the EX20 folder, and it basically shows how to combine parallel streams with and without the ManagedBlocker, and it uses the Java fork join framework to download and store images from a remote web server. Download and store multiple images from a remote web server. So here's the program. We go ahead, and when we run this thing, we parse the arguments. We create an instance of the EX20 class and run it. Here's what run does. And while we're talking, let me just go ahead and run this thing. So it can be cranking away while we're discussing. It takes a little while to do the work. We warm up the thread pool just because we want to make sure all the threads are active. And then we're going to run 3 different tests. One is going to use the download and store image behavior. That's the default behavior, as you can see here. That will download an image and store it. And if you take a look at download image, all download image does is it goes and downloads the content at a particular URL and encapsulates that content in an image object. Don't worry too much about what an image object is. It's just a container for the bytes in the file. So that's what download and store image does. And we run that test, and we'll time that. Next thing we're going to do is we're going to run a different example. This is a different function we're passing in. Notice behavior parameterization here. We're going to pass in something called download and store image MB for ManagedBlocker. And this is what the download and store image MB implementation looks like. We use an anonymous inner class here. Not my preference, but I'm just trying to show you the mechanism. We'll show a better way in a second. So we use the kind of somewhat sleazy trick of creating a 1-element array in order to be able to have side effects here. You'll see what we need that for in a second. And then we say fork-join-pool ManagedBlock. That's a special method that's only designed to work for the common fork-join-pool. And we make ourselves an anonymous inner class instance of ManagedBlocker. And ManagedBlocker has 2 methods, block and is releasable. Because it has 2 methods, that's why it's not a functional interface, so we can't get away with clever Lambda expressions or method references here. We have to do an anonymous inner class style approach, or we choose to do an anonymous inner class style approach. And the most important method here is the block method. And you can see what the block method does is it goes ahead and it downloads the image, and it stores it into this 1-element array of images. So we can get to it here and store it. But the key point is when the block method is called, this is used by the common fork join pool And it says, aha, this call will block. And if the call is going to block, then I, the common fork join pool, need to fork a new worker thread and add it to the pool temporarily, because this thread's going to block. And then that way, if there's other threads that need to run that are not blocking or just need to run, whether they block or not, then that will go ahead and those other tasks will get their chance to run because I've made a new thread to compensate for the fact we have one that's blocking. And then later, you don't see this here, but later the common fork join pool says, gosh, now I've got 43 threads in my pool, but nobody's been using them for the last minute or so. I'm just going to start shutting them down until I get back to the default number, which is, in this case, probably 15. We'll have to see when we run it how many cores this was known to the JVM. So that's the download and store image MB implementation. The third and final implementation is called download and store image BT, where BT stands for blocking task. And you'll see that blocking task is a really cool little wrapper class I wrote that is way less convoluted than this gobbledygook. And what it does is we say, blocking task, go ahead and do your magic under the hood in order to take this supplier lambda and download the image. So we'll take a look at what call in ManagedBlock does in a second. But I think you'll agree with me that this code is a heck of a lot simpler than this code. And that's because we wrote a little helper class to wrap up the behavior of ManagedBlocker. So let's go take a look at call in ManagedBlock. So here is call in ManagedBlock. You can see that blocking task is a helper class. You can read more about this concept here at this Stack Overflow link. This is just a lightly edited version of what's at Stack Overflow. And you can see we have the method call in ManagedBlock, which is a static method that's generic. So it takes a supplier to some type T, and it wraps that supplier parameter up in a nested class called supplier managed blocker. We'll look at that in a second. And then it takes the supplier managed blocker object, called it ManagedBlock, and it says fork-join-pool, call the ManagedBlock method on the ManagedBlock variable. So it hides all that gobbledygook that we had in the anonymous inner class in the previous version. And then when we're done, if all goes well, we just get the results that are stored here. So let's go take a look at supplier managed blocker. Supplier managed blocker is a nested class that implements the managed blocker interface. So that's where it gets the mojo to do its thing. It has a supplier field, a result field, and a done field. The constructor stashes away the supplier parameter in the local field. And then the block method will go ahead and call the get hook on the supplier field. Remember, get in a supplier will do whatever you told it to do. In our case, that's going to go ahead and download the file. That's what's hidden by get. That returns a result, which we stash away. We indicate we're done. And then the get result method just returns the result. So that's basically what blocking task does. I think it's pretty cool. And you can see how that makes this code very short and sweet. So now that we've kind of talked about the different implementations, I will show you another thing real quick because this is kind of cool. I have this little helper method called run test. Let's go look at the run test method. The run test method takes in the function, remember either the download and store image MB, or download and store image BT. Those are the different implementations we had. And the first thing it does is it garbage collects so that we start out with a pristine, fully charged memory heap for our program. And then we use a little helper method called time run on the run timer class. And if we go take a look at time run, what time run does is it takes in something like a supplier or a runnable or whatnot, and it goes ahead and starts the timing, calls the supplier get method or the runnable run method, waits till it's done, stops the timer, and then it sticks the test name and the execution time in what's called the results map. So it has a map internally that it uses to keep track of the results. So that's how we time this thing, and then we just call test download behavior, passing in the function, and you can see test download behavior does the following. It deletes any images that are left over from the previous run, and then it goes ahead and gets a list of URLs that we want to download, and you can see the URL list here is this list of image names. You can see I have a whole bunch of image names. These are all images that are stored on my website. And we then download them in parallel. We tell it to use the download and store image function, whatever that one was, which of the 3 different variants it was. And when we're done, we collect all the results into a list of images, and then we print the results. So if you go look at the results, these are the results. And lo and behold, we see the same results for this run that we saw when I ran this years ago, except now it's faster because you can see I've got 16 cores as opposed to 12 cores, which is what I had when I did those slides back in the day. Again, you can see how the default behavior uses 16 threads because that's the number of things in the pool, whereas the other ones use more because it adaptively grows the pool. And not surprisingly, because of the fact that we have more threads involved, the adaptive approaches work better than the default approach. So just kind of giving you an illustration of how using managed blockers can actually make a difference in terms of how well your program will perform, because it's able to do more work rather than having threads just sitting around bored, blocking and waiting for stuff to do.